Welcome to penphysics. As I said in the previous video, this is a series of videos in which I'll be solving physics IB past papers. And today I want to do a thermal physics problem, standard calorimetry. And for that I will use a pen which I got yesterday in my mailbox from a company in the US called Goulet pens. They do have a nice package. This is a very nice company in the US, very nice people, amazing service. They send things very fast, and you can see the package. This is the name of the company, Goulet pens, highly recommended. So they occasionally throw some gifts like ink and the lollipop. They always do that. It's pretty cool. Okay, so the pen is actually an order for a friend of mine, and I got his permission to use it, open it, fill it with ink, and do physics. It is a Pilot Falcon. So let me open it. Comes with an extra fine nib. And what I like about these pens is that when they come with a converter piston, so I can fill it with ink and I can put ink that I like. Today I will use stone gray from Faber. It's a very nice ink, not very black, it's grayish. And look at the container. It's like a perfume. It's pretty cool. Okay, so let me use this. Draw some ink. And it's okay to get your hands dirty. That's the whole point. It's the beauty of it. Okay, so that's full with ink. Put the cap back. Put the ink aside. And we're ready to go. That's it. Okay, so let me go to this May 2004. It's part B, question B3, it's part 2. It's melting of ice. So let me see if I can zoom it a bit. Okay. And I will even take some ink off. Alright, quantity of crushed ice removed from a freezer, placed in a calorimeter. Thermal energy supplied to the ice at a constant rate. This is important. This is power, energy per time. So that's a constant power. To ensure that all the ice is at the same temperature, it's continually stirred, etc., etc. What's important is to look at the graph. Here you have theta in degrees Celsius, that's the temperature. Here you have time in seconds. And you can recognize three stages. First of all, the ice is heated from minus 15 to 0 degrees. Then you have a region of constant temperature that is for the ice to melt. And then all the ice has been converted into water, and then the water is heated. So you continually provide energy, thermal energy, to do this. First question is, on the graph above, mark with an X the data point on the graph at which all the ice has just melted. So that's a simple answer. This is the point where all the ice has melted. Explain with reference to the energy of the molecules the constant temperature region of the graph. So this is this region here where the temperature is constant. Okay, so what is happening to the energy of the molecules? Well, first of all, you provide thermal energy. Okay, so let me write this. Thermal energy provided to, now all the thermal energy provided, it goes to increasing the potential energy of the molecule. So what's actually happening is that the molecular forces weaken or loosen. Nothing happens to the average kinetic energy of the molecules. Why? Because this is proportional to temperature, and the temperature is constant. So the thermal energy provided to increase the potential energy of the molecules. Okay, and I can put in parentheses even that intermolecular forces weaken. Okay. Throw some keywords to the IBO guys, impress them. Intermolecular forces. All right. Nothing happens to the average kinetic energy. Average kinetic energy remains constant because, and so that you know this, because it is proportional to what? To the temperature of the substance. Okay, so I think that's enough information for that. All right, let's continue. The mass of the ice, 0.25 kilograms. Specific heat capacity of water is 4,200 joules per kilogram per Kelvin. The first question is, deduce the energy supplied to the ice at a rate of about 530 watt. So this is the power. And we're given the mass of the ice and the specific heat capacity of water. But we know that the mass of the ice is the same as the mass of the water. So this was tricky, but we really have to look at this region because we have water, we know the specific heat capacity of water, and the mass is the same, power is the same in all regions, in all three regions. So we can use one of the equations, one of the formulas in calorimetry that says the thermal energy required to raise the temperature of water, for example, is equal to mc delta theta, where m is the mass of ice, C is specific heat capacity of water, delta theta is, well, from the graph, this is 15 degrees. Okay. But this thermal energy is the constant power times the time, which is what? 195. Every little square is 5 seconds. So this is 195 minus 165. So 30 seconds. So I can now just solve for P. P is mc delta theta over the time. This is 0.25 kilograms, is the mass of ice. C is 4,200. Delta theta is 15 degrees. And the time is 30 degrees. Okay, and you really have to do this calculation with the calculator, the GTC. Okay, don't just fake the result because you know it's 530. Do the calculation because you will find 525 watt, and then you can round it to two significant figures because that's the least in your calculation. Okay. And that's it. Done. 3 marks. Determine the specific heat capacity of ice. Okay. Since I'm looking for the specific heat capacity of ice, I need to look at this region. So this is the region where ice is heated, goes from minus 15 to 0. So delta theta is 15 in absolute value. And again, I need some thermal energy to do this. This is M, same mass, C of ice, delta theta of ice. And again, this is the constant power times the time, which is now, well, let's see, 5, 10, 15 seconds. 3 little squares. Okay, so what do we need? We need to find the specific heat capacity of ice. So this is the power, the time, the mass, delta theta. I know the power is 530. The time goes 15. Mass 0.25. Delta theta 15. You can cancel that. So again, you have to do this with a calculator to get 2120 units of specific heat capacity, joules per kilogram per Kelvin. And again, I need two significant figures, so 2100 joules per kilogram per Kelvin. And that's that. One more question, part 3. Determine the specific latent heat of fusion of ice. So now the other formula in calorimetry is for the change of state. Latent heat of fusion is Q over M, thermal energy over mass. Okay, and I need to work in this region that takes 150 seconds, 165 minus 15. So again, Q is equal to L times M. And this is equal to the same power times these 150 seconds. So what do I want? I want latent heat of fusion. So LF is equal to power times T, that's the energy, divided by mass. So this is easy, 530 times 150, 0.25. Do this calculation again with a calculator. I need to show my work. 318,000 joules per kilogram. I can round this to two significant figures and I can use the thousands as a kilojoule. So this is 320 kilojoules per kilogram. That's it. Thank you.